First off, I'm going to talk a little about the history of this symbol that you see above. So, the symbol right there is known as del, and it is the symbol we use to denote vector differentiation. And it actually has two correct names, the first being del, and we call it del because of its simplicity and the similarities, of course, to the symbol delta, because it really is just an upside-down triangle. And its original name was nabla, named after the Greek word for heart, but that name was thought to be, pretty inefficient because it was often found in long equations, and, just saying like del cross del f is a lot easier than nabla cross nabla f. And that's essentially why we call it del now. And the symbol was popularized in the mid to late 1800s by physicist Peter Tate, shown on the top left, and was utilized heavily in the vector analysis as well as the study of electromagnetics. Other people who were instrumental in the popularization of the del symbol include William Thomson, shown in the middle, Oliver Heaviside on the left, and of course James Maxwell on the right. So, what does the symbol del mean? When I took my first physics class, I'd sometimes see the symbol in various formulas, and just like the first time I saw the integration symbol, I was kind of scared, because I thought it was going to be a whole new concept that would be almost impossible to grasp from a conceptual standpoint. And if anyone else is a physics or engineering major, and especially if you're going to take or are taking 4B right now, you probably know that the del operator is essentially fundamental in that field, and not having a working knowledge of it is a pretty big handicap in terms of your ability to grasp concepts and work problems. So eventually I just decided to learn this stuff on my own because it was in my physics books, and as it turns out, it really isn't hard at all. And for the vast majority of situations, the del symbol is literally as shown here. It's just the partial derivatives along some set of standard bases. So the I, j, and k unit vectors can be replaced by whatever standard bases you want. And of course we can extend this upwards into higher dimensions. You got x, y, z, and so on and so forth. Note that on its own the symbol has no real meaning, and it must act upon something. It's not a vector in its own right. It's a command to differentiate something. And we already know three basic ways to multiply vectors, and we can relate these to the three most common uses for the del operator. For instance, a vector can be multiplied by a scalar to obtain another vector, and similarly, the del operator can act on a scalar function to obtain a vector. And of course, two vectors can be dotted together to obtain a scalar, or in the case of cross product, we'll obtain a vector by crossing two vectors. And in the next several slides, I'm going to talk about these operations and some of their applications. I'm not going to really show that many examples, as for the most part using the operators is simple, and there's just one formula for each thing, and there really isn't much thought to it. And in order to really get how everything ties together, you really need to know about vector function integration theorems. So I'm going to be trying to explain these in the simplest way possible without involving any integration. So the first thing we're going to talk about is the gradient of a scalar function, which for some function, f of x, y, and z, with unit vectors I, j, and k, is given by the equation shown here. It's quite simple, as all you really need to do is take the partial derivatives of your function and recognize that each component has a direction. Perhaps the easiest way to explain how gradient works is by the temperature example. So, say that we have some room and we have a function for the temperature at any point in the room, and we want to know how fast the temperature varies. Well, this causes a problem because the rate of change of temperature could be different for each of the infinite directions we might choose to explore. Perhaps the ceiling is extremely hot while the floor is rather cold, or maybe one side of the room has a heater. In order to get around this problem, we use a theorem for partial derivatives. Notice that we can now rewrite this as a dot product of the partial derivatives of t and some infinitesimal displacement vector. This is, of course, the same as the dot product of the gradient of t and our dl vector, which will give us the rate of change of t for whatever direction we choose. Now, if we write this in geometric form, using what we know about the dot product, we get this equation. Imagine then that we keep the magnitude of dl constant and vary theta. we notice that dt is maximum when dl is parallel to the gradient of t. This tells us two things. Firstly, that the gradient always points in the direction of maximum increase. And secondly, the magnitude of the gradient gives us the slope along that direction. Here's a graphical depiction of the gradient. We have a surface, and you can imagine it being a mountain or some hill for simplicity, and our gradient vector is denoted by this green line. Rotating about the same source point, we have a rotating unit vector along the curve. Changing the unit vector changes our tangent line along the unit vector as well as the trace along the curve. Notice that when the unit vector and the gradient vector lie on the same line, the tangent line to the curve has the greatest slope, which is to be expected, since the gradient points in the direction of maximum increase. Next up, we're going to talk about divergence, which is somewhat more complicated to grasp than gradient, but just like gradient, the notation of divergence can be written either way. You know, div f del dot f as opposed to grad f or gradient f. The way it's calculated is pretty straightforward in my opinion, and while you can't really say that divergence is the dot product of del and the vector function, since del is an operator and not a true vector, but this notation is what is most commonly used, and simply dotting the two together will get the right answer. And to understand the physical significance of divergence, we consider some vector function. So each point in space has a unique vector associated with. Now, imagine that we pick some point in space, and we imagine some volume that encloses the point. The ball in this diagram is such a volume. Notice then that the vector field lines will either enter the sphere or exit the sphere. This is known as the flux through the surface. Field lines that go into the sphere contribute a negative flux, while field lines that exit the sphere contribute a positive flux. The flux itself is directly proportional to the magnitude of the vectors that are going into or out of the surface. In this example with the ball, the divergence would be obtained by shrinking the ball to an infinitesimal size and measuring the net flux out of the ball. And for the ball, since the vector magnitude increases radially from the center, the divergence is positive for all points. If we were to flip the vectors in the example so that they were pointing inward, then we would have negative divergence. And if a point has positive divergence, that means that more field lines enter than exit, and we call that point a source. On the other hand, a negative divergence has more field lines. And here's an example that's pretty good for flux. If we assume that in this diagram here there's just some sort of surface, imaginary, surrounding it, and the red dot is positive and the blue dot is negatively charged. We know that electric field will point inward for the negatively charged particle and outward for the positive particle. And electric field lines are going to diverge positively in those examples if you have a positive charge and negatively for a negative charge. Now we're going to talk about curl. And to find the curl of a vector field, simply cross del with said vector field. And of course you can use matrix form or just memorize the formula if you really want. I mean, either way works. And it's used in a lot of computations and pretty easy to work out. The direction is obtained by using the right-hand rule, of course, and all in all it's pretty simple. But understanding what it signifies is a bit more challenging. Without getting into too much 1D topics, we can think about curl by imagining a ball floating in the ocean. If the ball rotates, then the field at that point has a non-zero curl. The vector field at the ball's location curls around some point, if it has the non-zero curl. In the example on the right, we see a depiction of some sort of circular vector field, and there are blue circles that are clearly rotating around different orbital points. And if you notice, the vector length, and consequently magnitude, as that's what it represents, increases the more radial distance you travel from the center of. So this means that these circles, the blue circles, are going to have some sort of clockwise rotation, and thus the direction of curl is going to be out of the diagram. Now let's consider the diagram on the left. In the graph shown, we have some vector field f equals negative x squared in the y direction. Let's just take it to be the current in some liquid. Note that although the vectors do not twist, if we were to place a ball of, say, diameter 2 between x equals 2 and x equals 4, then the ball would in fact begin to rotate clockwise due to the larger current at x equals 4. It's a lot like torque if you think of vectors as forces. The tangential components along the ball's surface will cause a rotation. Note that just because an object moves along a circular path doesn't mean there is a curl present. Curl is a measure of local rotation. In this example, the curl would be given by negative 2x in the z direction. When x is positive, the curl is into the page, and vice versa for negative x values. Just like how divergence measured the flux through an infinitesimal volume, curl measures the circulation, which you can think of as the amount a vector field pushes along a path over an infinitesimal area. It's worth noting that any vector field with non-zero curl is non-conservative, and if a vector field has zero curl, it can be represented as the gradient of a scalar potential. When you think of curl, an obvious real-world example would be the case of a vortex. And indeed, the study of weather systems as well as fluid mechanics both involve the study of curl of some flow velocity. In these fields, there is a pseudo-vector field known as the vorticity that is defined as the curl of said flow velocity. Now, before talking about what this quantity means, let's find the vorticity if we have some flow velocity given by this equation. Now, to find the vorticity, we must use our formula for curl. And we see that when we cover up the I column in row, we will get 0, and the same goes for j. But for k, we see that our curl will have some value. The partial derivative of f sub y with respect to x is 0, leaving us with only one term. So, we know that for the flow velocity we have chosen, there will be a vorticity present, and hence we have a rotational flow. If the vorticity was 0, we would have had an irrotational flow. So, we have a non-zero vorticity, but what does that really mean? Well, vorticity describes the local spinning motion for some point, and local spin just means an object tends to rotate. With that understood, we look at the two animations and ask ourselves about the curl present. At first, you might think that since the circles shown are both rotating about some point, then in both cases we'll have a non-zero vorticity. However, if you take a look at the bisecting lines of the circles in both figures, you will notice that for the animation on the left, these lines do not change directions, and this is not the case for the animation on the right. This tells us that we have no local spin in the left figure, and thus the vorticity and consequently the curl are both 0, making the flow velocity an irrotational conservative field. A whirlpool is an example of an irrotational vortex, where the flow velocity is inversely proportional to the distance from the center. Shown here are Maxwell's equations, both in del form and in their original form. And as you can see, the use of del greatly simplifies the notation for many of these physical rules and laws. Now, I'm going to show you an example of a physics problem that requires a knowledge of curl and divergence, related directly to Maxwell's equations. It's fairly complicated, so don't worry about understanding its exact meaning. The point of the derivation is to show how curl and divergence are basically the core building blocks of the study of electric and magnetic fields. So, say we have some volume, and we want to determine the total electromagnetic force on this volume. We're going to need to use Maxwell's equations as well as the Lorentz force law to solve this problem. The total force on the charge is given by this equation, where Q is the charge value, E is the electric field, V is the velocity, and B is the magnetic field. So, if we want the total force on some volume, we're going to need to create an equation for the force per unit volume and then integrate over the entire volume. So, let's substitute rho, or charge density in this case, for Q, where V becomes J when you multiply by rho. Looking at Maxwell's equations, we see the first equation involves rho, and we can isolate it and rewrite it as such. Similarly, the fourth equation involves J, and we can isolate that as shown. Now, we plug both of these into our original formula. Next, we want to eliminate this partial derivative. So we use our knowledge of differentiation of a cross product and rewrite it as so, also applying the third of Maxwell's equations. And additionally, we're going to choose to add this factor, since by equation 2, it has to be 0. So, and don't really worry about why we add this. We're just adding for the sake of symmetry. So now we plug all of this back into our equation, and we're going to obtain something rather complicated. We have one more step, and that is to use a vector calculus identity to eliminate the cross product with curl terms for E and B. And our final equation holds a rather neat symmetry in terms of E and B, and despite its length is rather easy to calculate given E and B. It turns out that the term on the right, in red, the cross product of E and B, can be rewritten using something called the Poynting vector, which describes the energy in electromagnetic waves. The terms in blue turn out to be the divergence of the Maxwell stress tensor, so the entire equation simplifies as shown. And it might not seem like it, but certain problems become much easier through the use of this formula. And again, it's not much, you don't have to understand what the equation means. I mean, it's essentially just a fairly long algebra problem involving a lot of differentials. But the point is, without curl and divergence in the del notation, you couldn't do it. And the last sort of fundamental operation involving del is known as the Laplacian, and it is given as the divergence of the gradient of some scalar function, and it's typically simplified and as shown. And in essence, it's just the sum of the second-order partial derivatives. As with most of the del operations, if you have a scalar function, it's quite easy to calculate the Laplacian. There is also a vector Laplacian, but it's not calculated in the same exact way, and it gets rather complicated, so we won't talk about that. One special case that involves Laplacian is Laplace's equation, which basically says that Laplacian is 0, and Laplace's equation is a second-order partial differential equation, and functions that satisfy it are harmonic. An interesting case is the Laplacian for a function of one variable, which will have a solution in the form y equals mx plus b, which is, the equation for a line. Laplacian is mostly used in wave theory as well as quantum mechanics, but it also shows up here and there in mechanics and electromagnetics, and some equations that utilize the scalar Laplacian are Schrodinger's equation and the wave equation, and another case where the Laplacian shows up is in Poisson's equation. And in the example shown, it's Poisson's equation in terms of gravitational potential. But the right side of the equation can be any arbitrary scalar function as well as some constant, and analogously there is one for voltage in terms of electromagnetics.
This is a three-dimensional graph, which means that it's representing some kind of function that has a two-dimensional input and a one-dimensional output. In mathematics, we would represent it as f of xy equals some expression that consists of x's and y's. It can be clunky or difficult to do by hand on the fly, but contour maps provide a simple way to represent the function in two dimensions. Why? First, we start with the graph of the function. Then, slice the graph with a few evenly spaced level planes, each of which should be parallel to the xy plane. You can think of these planes as the spots where z equals some given output, like z equals 2. Then mark the graph where the planes cut into it. Now, project these lines onto the xy plane. We'll get a contour map. In other words, you choose a set of output values to represent, and for each one of these output values, you draw a line which passes through all the input values x and y for which f of xy equals that value. Now let us try an example. Identify the level curves off of xy equals the square root of x squared plus y squared. Here is how we do it. First we set z equals square root of x squared plus y squared. When we square both sides, we'll get z squared equals x squared plus y squared. By looking at this equation, we'll find that this is a cone, because the square root will only return positive numbers. It seems like we only need the upper half of the cone. The level curves for this surface are given by the equation are found by substituting z equals k. So, in this case, the level curves are circles of radius k with their centers at the origin. Now, we know what the graph looks like in 3D. Following the steps we just mentioned, we'll get the graph in a two-dimensional axis system.
Now we will talk about Lagrange multipliers. Lagrange multipliers, also known as Lagrangian multipliers, are a method that is used in mathematical optimization for finding the local maxima and minima of a function, subject to equality constraints, as you can see explained above. The Lagrange multiplier is used to find the extrema of multivariate functions of x, y, z, subject to the constraint that g of x, y, z equals 0, where both f and g are functions with continuous first partial derivatives on the open set containing the constraint equation with the gradient of g non-zero. Now we will discuss how to employ the method of Lagrange multipliers. So, to find the maximum and minimum value of f of x, y, z, subject to the constraints g of x, y, z equals k, we assume that these values do exist and that the gradient of g is non-zero for any point on g. First, we have to find all values of x, y, z, and lambda, such that gradient of f equals the product of lambda with the gradient of g, where g of x, y, z equals k. Second, we evaluate f at the point we find from part A. The highest value would be the maximum value and the lowest will be minimum value. Now let us try some examples. Find the maximum value of f of x, y equals xy subject to the constraint that 2x plus y equals 4. Our first step is to find the partial derivatives of f with respect to x and y, which will equals the partial derivatives of g with respect to x and y, multiplied with lambda. After that, we obtain the equations y equals 2 lambda and x equals lambda. Therefore, we know that 2x equals y, and we can substitute them into the constraint to get 2x plus 2x equals 4, which means x equals 1, y equals 2 and lambda equals 1. If we plug this back into our equation, we will see that f equals 2 is our maximum. Now, let's attempt another example. Minimize x squared plus y squared plus z squared, subject to the constraint x plus y plus z minus 6 equals 0. The steps are the same as in the last example. We need to find the partial derivative of f and g with respect to x, y, and z. Once we do this, we would see that 2x equals lambda, 2y equals lambda and 2z equals lambda. Therefore, x, y, and z are equal. Substitute this into the constraint x plus y plus z equals 6, and we find that x, y, and z equal 2, while lambda is equal to 4. Plugging this back into our original equation will obtain our minimum value, which is 12. Thank you for listening and I wish you all good luck for final week.
Tangent plane and linear approximation. When we have a 3D surface, we can pick a point on that surface and make a tangent plane of it. This point has a particular normal vector. This normal vector can be written as follows. The left symbol is del operator, while the right symbol is a scalar function. Normal vector of the 3D surface can be obtained by using this formula. What is the advantage of knowing equation of tangent plane? When we are asked of coordinates that are not simple number and the algebra will be difficult, we can obtain an equation of tangent plane and pick a coordinate near it and make approximation. Let's do an example. Approximate z when x is equal to 1.2 and y is equal to minus 0.1 of this function. Our first step is to use the formula, differentiate and get the normal vector, and plug in the known values. Make use of the normal vector to make the equation of tangent plane. And we get the equation and plug in the as coordinate and get the approximation.